Have you ever wondered why the condensate returning to the boiler carries so much steam? Is that normal or abnormal? Does your factory have many steam-using machines, but each machine heats up differently, some fast, some slow? Have you ever noticed your equipment has a steam trap assembly, but the bypass valve is always open? There are many similar issues as well. Today, I will summarize over 15 years of real-world boiler experience to share with you. These are common mistakes that most factories encounter. I hope this video is useful for you. If you find it helpful, please share it with others. I believe this video will help your factory save significant operating costs and reduce environmental emissions. My philosophy is that keeping knowledge to yourself is like running a boiler without blowdown. So let's begin sharing. If anything is missing, feel free to contribute. Here are the 12 common mistakes related to steam traps. Mistake number 1. Choosing the wrong type of steam trap, as mentioned in previous videos. If the equipment has a stable load and uses a control valve to regulate steam, an inverted bucket steam trap should be used. If the load fluctuates and steam flow is modulated by a control valve, use a float steam trap combined with a thermostatic air vent. For discharge points without control valves, such as steam headers, steam lines, or end of line, use a thermodynamic trap. Many factories use the same type of equipment, but install different traps at different points, thinking a trap is a trap, when the operation is unstable, not knowing the reason why. Therefore, choosing the correct steam trap is the key prerequisite for a stable system. In the upcoming videos, I will compare the real operating behavior of each type of steam trap. You just need to watch and you will understand immediately. Mistake number 2. Not calculating the correct discharge capacity of the steam trap. Normally, the design team and the heat exchanger manufacturer already know the steam demand of the equipment and the amount of condensate that needs to be discharged. These average values are usually fairly accurate. But have you ever thought that when the equipment has just started up, the amount of condensate can suddenly spike? When a new production batch is introduced, the equipment requires more heat and produces more condensate. That's why I recommended in the previous video, choose a safety factor of 2 to 3 times compared to the design value. If the load fluctuates continuously, but if the load is stable, then a safety factor of 1.5 times is enough. If the safety factor is chosen too low, there will be many moments when the steam trap cannot discharge condensate in time, leading to condensate accumulation. The machine heats up slowly, heat transfer, efficiency drops, and overall efficiency decreases. When condensate backs up, operators often open the bypass valve to heat up the equipment faster. However, once the bypass is opened, steam flow rises suddenly, and many operators leave the valve open. This causes a large amount of steam to return to the boiler. Regarding how to select steam trap discharge capacity, please rewatch the previous video, Understanding Steam Traps. Part 2, I provided a specific example in that video. Mistake number 3, not accounting for differential pressure or not fully understanding the concept of pressure differential. When talking about ΔP, many people still don't understand it clearly. Let me explain briefly. The condensate pressure must be high enough to push the condensate through the steam trap into the main condensate line and send it back to the boiler. There are many pressure losses along the pipeline. If the condensate needs to rise 10 meters, then at least 1 bar of pressure is required. This does not include friction losses from pipe friction and elbows along the condensate return line back to the boiler. If the pipeline has no natural slope, or if the pipeline is too long, friction loss will increase, making the total pipeline resistance much higher. Therefore, for the condensate to return to the boiler, the pressure after the steam trap must be high enough to overcome the total pipeline resistance from the trap to the boiler. For example, condensate from the steam trap must be lifted 5 meters to reach the main condensate line, equivalent to at least 0.5 bar pressure loss. The main pipeline is 100 meters long. Horizontally, assuming friction loss is around 0.5 bar, then the total minimum loss is 1 bar. The steam trap assembly includes a shutoff valve, strainer steam trap, and check valve. When the piping passes through heat exchange equipment, the pressure loss increases and can reach up to 4 bar. Therefore, the inlet pressure must be at least 5 bar. ΔP equals 4 bar. If the trap is selected based on a 3-bar ΔP, its actual discharge capacity will decrease during operation and fail to meet the system requirements. leading to incomplete condensate discharge. Perhaps up to this point, you may find it a bit confusing. Most factories do not understand this issue clearly. Therefore, you should work closely with a piping design team knowledgeable in steam systems, with deep expertise in steam engineering, to achieve an optimal design. Next is mistake number 4, incorrect installation position. This is a common mistake. Basic principles must be followed. Water always flows to the lowest point. Many technicians think that they can install the steam trap at a high point and send it through the steam trap. This is partly correct and partly incorrect. For example, in this picture, the steam trap is installed at a high position. Condensate will definitely accumulate at this location. Case 1. Condensate accumulates at the lowest point, creating a blockage before the trap, causing flooding, reducing steam trap performance. The trap may even fail if it lacks automatic air venting. Case 2. Condensate remains inside the pipe, reducing heat transfer surface area, lowering equipment efficiency. Case 3. Steam and condensate mix and enter the trap, causing water hammer. If the system was originally designed this way, there are 2 solutions. Option 1, create a low point drain and install the steam trap there. Option 2, extract condensate at the lowest point using a branch pipe, which is a sub-pipe inside the heat exchanger. Have you ever encountered this problem? Do you have questions about any other mistakes? Stay tuned for the next videos from DIVI.